Now there is one other technique that is very popularly used to realize high-speed ADCs. And the idea behind this technique is the following. So let's say you have an ADC that you have designed. This could be a flash ADC or any other ADC structure that we'll discuss later in the courses. So let's say this ADC can digitize the signal at a rate 1 gigasamples per second. That is, it can digitize 1 million samples in 1 second, right? But now let us say your target is to realize an ADC that can do the job at 2 gigasamples per second, right? And you find that you're not able to redesign and improve the speed any further than 1 gigasamples per second. But let's say you have 2 such ADCs. Can you think of a way to do this job where we need to have an overall ADC that can digitize the signal at 2 gigasamples per second? Again, please pause the video and think. Well, if you have 2 ADCs, what we can do is the following. So each individual ADC here can do the digitization at 1 gigasamples per second, right? So if you just use one ADC, it can do the digitization at say 0, 1 nanoseconds, 2 nanoseconds, and so on. But what we need is also these points, right? We need to digitize the input at these time instants as well, 0.5, 1.5, and 2.5, and so on. Okay. So what we can do is we can take the first ADC, make it sample and digitize at 0, 1 nanoseconds, 2 nanoseconds, and so on. Use the second ADC to do these digitizations, right? Again, remember that these are still spaced at 1 nanoseconds, but the timing instants are just offset by 0.5 nanoseconds. Right? So now if you take these two outputs and switch between them, okay, so you take the first output you'll take from this ADC, that is this. Second output you'll take from this ADC, that is this, and you keep switching between them. Then overall, this entire box will look like an ADC that is operating at 2 gigasamples per second, right? So the same input is given here, right? But the clocks to these two ADCs are offset by 0.5 nanoseconds. Okay. So doing this will help us improve the overall speed. In general, if we have 2 such ADCs, each having a capacity to sample and digitize at say 0, 2 TS, 4 TS, and so on, we can have the second ADC operating with a time offset of TS. So this will be running at, this will be sampling at TS, 3 TS, 5 TS, and so on, right? So by combining these two outputs, we can overall get an ADC sampling at Fs, although the individual ADCs are operating at a rate of Fs by 2. Okay, and this technique is called time interleaving. Because you essentially are interleaving these two ADCs, right, and taking the output from the two of them, right? And here we have a 2x time interleaving, where we have just two ADCs, right, and these two are interleaved. And this technique obviously can be extended to n ADCs also. So in general, let's say you have n ADCs, each having the capacity to operate at Fs by n. If you have n copies of them, and make sure that the first ADC samples at 0, NTS, 2 NTS, and so on. The second one at TS, n plus 1 TS, and so on. Similarly, the last one will be doing at n minus 1 TS, 2 n minus 1 TS, and so on. So in this case, you can switch between all these n ADCs, and overall you can realize an ADC sampling at a rate Fs, right? And this is called NX interleave. this interleaving is a very popular technique that is used to realize a high-speed ADC. Okay, and in the modern times, if you take any high-speed ADC, you will find that they use some kind of time interleaving. Okay, so now that we have seen this technique can improve the speed of the ADC, let's see what are the possible things that can go wrong in this. So let's now discuss the non-idealities, because obviously there is no free lunch, right? So there should be some issue with this. And to understand this, let's consider a simple 2x interleaved ADC. So I have the input that is getting fed to these two ADCs, and the output is multiplexed, right? And of course, this is sampling at 0, 2TS, 4TS, and so on. This is sampling at TS, 3TS, 5TS, and so on. So this is doing the job at even time instance, and this is doing the job at odd time instance. Okay. So first thing which can go wrong is that, well, here both the ADCs will have offsets, and obviously the offset will not be same for both the ADCs, right? Because offset is something random, and as we saw, the physical or the reason for having an offset is mismatch between the transistors, and this is a random phenomenon. So we'll have two different offsets. So let me just show it in another color. So let's say the first ADC has an offset POS1. This has an offset POS2. The second thing, of course, is both of them might have some gain error, right? So, and these two gain errors will obviously be different. So let's say this has a gain error K1, this has a gain of K2. And the last thing is here, ideally we assume that the timing skew between these two ADCs is exactly TS, right? Because if this is operating at 0, 2TS, 4TS, this should exactly operate with a time offset of TS, right? So this is now TS, this has become 3TS, 5TS, and so on. But obviously, in practice, there will be some offset, timing offset error. So instead of sampling at TS, 3TS, 5TS, so on, the second ADC here might sample at TS plus delta T, 3TS plus delta T, and so on. Okay, so let's quickly see what effect these non-idealities have and see how we can overcome them or try to suppress them. So first, let's look at the offset error. So what will happen if the offset is there? So for considering offset, we'll assume that we don't have any other non-ideality. We just have offset. Okay. So let's say the signal here is some x of t. So what will happen? Well, from the first ADC, the output, if I call it x1 will give samples which are x of 0, right? Of course, x of 0 is the digitized version of the signal x. So for simplicity, I'll just call it x of 0. So x of 0 plus VOS1, x of 2TS plus VOS1, and so on. The second ADC will give x of TS plus VOS2, x of 3TS plus VOS2, and so on. Right, so finally, when you multiplex between these two, the final output samples will be x of 0 plus VOS1. Next will be x of TS plus VOS2, right? And the third sample will be x of 2TS plus VOS1. This will be x of 3TS plus VOS2, and so on. Okay. So in this, these are the terms that we need, right? So along with it, we also have an error signal, and this error signal is this, right? So if you look at this error signal, if I call to be some E of n, how is it looking like? It is essentially VOS1 and VOS2 getting repeated periodically. VOS2, and it simply repeats. Okay. And obviously, if I plot it, it will look like this, right? So this is, let's say, VOS1, this will be VOS2, and so on, right? So this sequence can be decomposed as some of a constant signal, right? And what is the constant? That is the DC, which is VOS1 plus VOS2 by 2, right? And along with it, we also have an alternating sequence of ones and minus ones. But of course, it will not be exactly 1, and this will be VOS1 minus VOS2 by 2, right? And this will be minus of this quantity, okay? So what I have done here is essentially finding decomposing the signal in terms of its Fourier series coefficients, right? So since it has a period of 2 samples, you have only 2 signals or 2 frequency components, right? So the period is 2. So you have the fundamental thing as 2 pi by 2, right? So you have only 0 and pi, right? So the frequency components it can have is k times this. K equal to 0 corresponds to DC, that gives this. And k equal to 1 corresponds to a frequency of pi. And that gives this alternating sequence of ones and minus ones scaled by this quantity. Okay, so now how will the spectrum of this error signal look like? This is going to contain a tone at DC and a tone at Fs by 2, right? Pi corresponds to Fs by 2. Okay, so along with the signal, which can have a spectrum like this. Okay, so you also have 2 tones at DC and Fs by 2. Okay, so this DC is okay because even if you just had one single ADC that was operating at the full speed Fs, you'll still have an offset, and that would have given you a tone at DC. But this tone at Fs by 2 might be problematic because the signal could have significant strength at Fs by 2, right? So I considered some triangular spectrum like this, but in practice, the actual spectrum might look like this, right? So some spectrum like this. So which means the presence of this Fs by 2 tone might create issues. So we need to reduce the strength of this Fs by 2 tone that is arising due to the mismatch in the offset. And one way to correct for it is to go back and try to make sure these two ADCs are matched by good analog design techniques. But a much easier way is to correct it digitally, right? So what I mean is the following. So here I have the 2 sequences, right? X1 and X2, which are the outputs of the 2 ADCs. So now at the output, I multiplex them and I get the final full rate sequence. Okay. So what I can do is I can add a signal in the digital domain. Remember that these are digital samples, right? So digitally, I can add a sequence that is looking like this, right? So I can kind of add or subtract it from the sequence here so that this portion is completely cancelled, right? So the only thing I have to determine is the strength of this Fs by 2 tone, that is the strength of these ones. And that can be done by simply giving a test signal. So I have the two-way multiplexed, two-way time interleaved ADC like this, right? So these are the offsets. So this is X1 and this is X2. Okay. So what I can do is I can give a signal which could be a 0 also, right? I'll give a 0 signal, right? So which means at the output, I'll not have any contribution due to this. I'll have only the error signal. So if I look at the output spectrum, I'll have only 2 tones, one at DC, one at Fs by 2, right? And looking at the strength of this Fs by 2 tone, I can back calculate what should be the strength of this signal, and I can subtract it to completely cancel the effect of this offset. Okay, so this kind of digital calibration is what is most commonly used in these kind of mixed signal systems, because you will find that correcting the non-idealities in the analog domain will be much difficult, but the same could be done easily in the digital domain. Okay, so that's the advantage in these kind of mixed signal systems, where you can exploit the efficient computation that can be done in the digital domain, and this can be used to correct for any kind of non-idealities that will be there in the analog design. Okay, so now let's discuss the second non-ideality, which is the gain error mismatch. Right, so we have the two interleaved ADCs with two different gains. And one reason why you might have this kind of different gain error is that, remember that when the ADC is sampling inside, so the circuit is this, right? So you have switch and a capacitor essentially. So you'll have two structures like this, right? So this might be here and this might be here. Now, although in principle, these two capacitors that are used in the ADCs will be equal in value, in practice, they'll have some difference, right? And of course, this switch here, they'll also have some mismatch. So which means even the on resistance of the switches will be slightly different. So this could be R on 1, C on 1, and this could be R on 2 and C2. Okay, so even if you give a constant signal, say V naught, you know that the output will do V naught into 1 minus C power minus T by tau, right? And since the time constant tau is different in these two cases, at the end of the sampling case, instead of getting V naught, in the first case, you'll get some K1 times V naught. In the second ADC, you might get K2 times V naught. Okay, so this is one reason why you might have a gain error. And obviously, there could be multiple other sources, right? And they will all contribute to some kind of a gain error. So now let's see what happens because of this gain error. So again, let's say I give a signal x of t. What will happen? The first ADC that will give out output samples like this. So it will be k1 times x of 0. Again, remember, this is sampling at 0, 2ts, 4ts. This is sampling at ts, 3ts, 5ts. Right? The first sample will be from the first ADC. That will be k1 x of 0. The second sample will be from this ADC. That is k2 times x of ts. Again, the next sample will be from the first ADC. That will be k1 times x of 2ts. This will be k2 times x of 3ts and so on. Right? Now, this sequence can be modeled as having the ideal sequence x of n getting multiplied by a sequence which is looking like this, right? K1, K2. Okay. So again, this sequence comprising of K1, K2, that is the sequence is a periodic sequence with a period 2. So this can again be decomposed as a DC signal plus a tone at fs by 2. Okay. So now if the input has a signal component at fin, what will happen? The signal is getting multiplied by these two signals, right? So the spectrum will get shifted around these two frequencies, right? Because multiplication in time domain results in convolution in the frequency domain. So at the output, what you will have is two tones. One, fin will be shifted around DC, which is the same. So you'll have fin. So let me show it in green. We'll have one at fin. And you'll also have this fin shifted around fs by 2, right? So we'll have fs by 2 minus fin. Okay. So even though your input had only one tone, at the output, you'll have one at fin and one small tone around fs by 2 minus fin, right? So this is fin. Okay. And of course, the strength of this tone will depend on the strength of the fs by 2 tone. That in turn depends on k1 minus k2, right? Because obviously you saw it from here, the strength of this fs by 2 tone depends on the difference between these two. So here also it will be dependent on the difference between these two values, right? So if the gain values here are very close to each other, the strength of this tone will be small. And if they are grossly different, then you will have a high strength here. And how can we correct for it? Again, one way is to go and do the correction in the analog domain by trying to minimize the mismatch in the gain error. Again, but a much simpler solution is to do this correction digitally, right? By doing a digital calibration, where we can add a digital gain here, right? I'll call it some I don't know, A1 and A2. Okay, and I can tweak these values of A1 and A2 such that the gain error is reduced, right? So ideally, if A1 is say 1 by K1 and this is 1 by K2, you'll not have any gain error, right? Or you don't even have to have two gains. You can just have one here, right? So if the gain here, K2, is chosen to be K1 by K2, right? So what will happen? So here I'll have K1 times X. Here I'll have K2 times X. But here I'll have K1 by K2 times K2 times X. So which means I'll get back K1 times X, right? So there will be no gain error mismatch in these two parts. Okay. And of course, how do you find the value of this A2? Well, what you can do is you can give a tone at Fin, a single frequency, right? And at the output, after you multiplex, you look at the strength of the tone here at Fs by 2 minus Fin, right? And you have some digital logic that goes and tweaks the value of, let me just erase it. So it goes and tweaks the value of this gain factor till the strength of this tone is minimized. Okay. And of course, for this, you can use some kind of an optimization algorithm here, like least squares or something. Okay. And of course, we considered the case only for 2 channels, but if we have an n-channel case, what will happen? This sequence here will look like this, right? So it will have K1, K2. Well, let me just write it, that may be easier. So the sequence here will be K1, K2, K3, so on till Kn, and then it will repeat. Right? Because you first take the output from the first ADC and then go to all the n ADCs, and only after taking the outputs from all the n ADCs, you come back to the first ADC again, right? In an n channel or an nx time interleaved ADC. Okay, so now it looks like the output is getting multiplied by this sequence, right? And of course, this is a periodic sequence with a period of n samples. Okay, so if you look at the spectrum of this sequence, it will contain tones at multiples of 2 pi by n. So essentially, we'll have tones at Fs by n, sorry, 0, Fs by n, 2 Fs by n, and so on. Okay, so if you give a sinusoid at a frequency of Fin at the input, at the output, you will have this Fin getting translated around each of these frequencies. Okay, so you'll have a tone at Fin, you'll have Fs by n plus or minus Fin. Here you'll have 2 Fs by n plus or minus Fin, and so on. Okay, so again, to correct for this, what you have to do, so one way is to do this kind of digital calibration, right? So what you can have is, you have all the n channels. You can assume that the gain of the first channel is fine, and you tweak all the other n-1 gains. Okay, and you need to simultaneously reduce the strengths of all these unwanted tones. Okay, so you can have some kind of digital logic that looks at the strength of all these unwanted tones and tweaks all these gains so as to minimize the strength of these. Okay, again, even for the offset mismatch case, for an nx time interleaved ADC, the error signal here will be a periodic signal with a period of n samples. So you'll have tones at fs by n, 2 fs by n, and so on till n minus 1 fs by n. Okay, and to correct for it, you need to add or subtract the periodic sequence with a period of n samples. Okay, and of course, this is not the only way in which you can calibrate and correct the offset. I just told a very trivial or a straightforward way of doing it, but there might be much better, efficient ways of digitally estimating and correcting this offset mismatch error, right? Same for the gain error also. So this is not the only way, right? What I told is you apply a tone at Fin and look at the strengths of all these unwanted tones and tweak the gains to minimize it, right? This might not be the only way of digitally calibrating this gain error mismatch. There may be other efficient ways of doing this also. So let us now discuss the last non-ideality we might have in the interleaved ADC, which is the timing skew or the timing offset. The problem arises here because ideally we wanted the two ADCs here in a 2-channel or a 2x interleaved ADC to be operating with a timing offset of TS, right? So if the first ADC is running at 0, 2 TS, 4 TS, and so on, the second ADC must do its job at TS, 3 TS, 5 times TS, and so on. But in practice, this will not be the case because you might place the ADCs physically apart, right? They need to be physically placed apart. So which means if the clock is coming here, it might reach the first ADC with a shorter delay, but for the second ADC, it might be a longer delay. Okay, so this is one example or one reason why you might have this timing skew. So the actual sampling instance might be TS plus delta T, 3 TS plus delta T, 5 TS plus delta T, and so on. So let's see what will be the output sequence we get. So the first sample will be from the first ADC, that is x of 0. The second will be x of TS plus delta T. The third will be x of 2 TS. This will be x of 3 TS plus delta T, and so on, right? And of course, if delta T is small compared to TS, which obviously will be the case, this x of TS plus delta T can be expanded using Taylor series, right? And this is equal to x of TS plus delta T times x dash of TS, plus you will have higher order terms, which will ignore because delta T will be much smaller. Okay, so I will just replace this with the Taylor series approximation, that is x of TS plus x dash of TS times delta T. Similarly for this guy, it will be x of 3 TS plus x dash of 3 TS times delta T, right? So now, again, these are the terms that we want ideally. In addition to that, we have these two terms, which are the error signal or the error terms, right? So if I look at the error signal, that's going to look like this. It is 0, x dash of TS times delta T, 0, x dash of 3 TS times delta T, and so on, right? And we can see that this can be modeled as follows. So I take the signal x of t, multiply with delta t, that models this multiplication, and then take the derivative that models this x dash, and then sample at TS that models the derivative here, and then I'll multiply with the sequence of 0, 1, 0. Okay, so this will ensure that you don't have any error at these points. Okay, and from this error signal, you see that the error signal will be much higher if the input slope is much higher, right? And why does this make sense? Well, because if the input is changing very slowly, even if there is an skew in the sampling time instant, ideally instead of sampling at this point, if you say you sampled here, the error is very small, right? So this is the error in the amplitude. But instead, if the input is changing very rapidly, even if we have a very small error in the timing, in the sampling time instant, the corresponding error you incur in the magnitude is much larger. Okay. So now this is how we can model this error signal. So let's see what will be the spectrum of the signal. So let me copy paste it. So let's say I give a sinusoidal frequency Fn. So here also you'll have Fn. Even after the derivative, the signal frequency is going to be same. So this is getting sampled, and this sequence of 0, 1, 0, 1 can be decomposed as sum of a DC term plus a tone at Fs by 2, right? So if this is getting multiplied, what will happen at the output? I'll have a tone at Fn plus a tone at Fs by 2 minus Fn. Okay. So again, if the input has Fn, at the output I'll have Fn as well as a small tone at Fs by 2 minus Fn, right? So let me draw it also taller. Okay. So you can see that the error you get or the spectrum you get is very similar to what you had when you had the gain error mismatch, right? Even for the gain error mismatch, you saw that you got a tone at Fs by 2 minus Fn, right? And let's see how this timing skew error can be corrected. Well, there are two possible things that can be done. One is to notice that we are having this error because the signal is changing continuously throughout the sampling period, right? So what we'll do is we'll have a global sample and hold. Okay, so if the signal is varying like this, so this sample and hold will be operating at the full speed Fs. Okay, so the output here will be some kind of a sampled and held signal like this. Right? So if you look at, if I just zoom in here, the waveform might look something like this. Oops. Right? And this is then given to the two ADCs. Right? And the first ADC will be processing these samples, and the second ADC will be processing these samples. So now even if there is an offset or a skew in the sampling time instant, that is instead of sampling at this point, if you sample here, there will be no error you make. Okay, so this is one thing that you can do to avoid the error due to sampling or the timing skew. But of course, this is possible only if you can realize a sample and hold that is operating at the full speed, right? Because if you are trying to realize a very high speed ADC, it might so happen that you might not be able to realize a sample and hold operating at the full speed. And that might be one of the reasons why you are going for this kind of a 2x interleaved or an nx interleaved ADC. So if you cannot do this or afford to have a global sample and hold operating at the full speed Fs, so remember this operating at the full speed Fs, what can be done is the following. You can have the first ADC and the second ADC. And the clock to the second ADC might come from another clock, which generates multiple delayed versions of the clock. Okay. And you can choose which of these clock signals need to be used for sampling, again by doing some digital calibration, right? So I look at the output here, I'll apply a signal at Fin. So due to this timing offset skew, I'll have a tone at Fs by 2 minus Fin. Okay, so if this has only if this has only timing skew error, then the tone at Fs by 2 minus Fin will arise only due to this. So you can choose the multiple phases of the clock and see for which of them you get the minimum strength for it. But of course, in practice, you will have both gain error and this timing skew error. And remember that even the gain error will result in a tone at fs by 2 minus fp. Okay, so in that case, we can probably first correct for the gain error, right? And then let me say here, so do a block here, correct for the gain error, right? And after correcting for gain error, whatever residual tone that is at fs by 2 minus fin, that will be due to this timing skew. And then you can correct for the timing skew error, right? Or of course, you can do a combination of the two simultaneously to minimize the strength of the tone. And to generate multiple delayed versions of the clock, you can have a programmable delay line. And of course, you might be learning, or you might already have learned if you are taking the circuits for frequency and phase synthesis course. So you can essentially have an inverter chain or a buffer chain like this, and you tune the capacitor value. And of course, by tuning the capacitor value, I mean that you can have multiple capacitors like this, a capacitor bank, right? It can be weighted in a binary fashion, 4C8C, right? And you can put the appropriate number of capacitors here to generate the required delay. As I mentioned earlier, interleaving is the commonly used technique to realize high-speed ADCs nowadays. And in principle, there is no limit to this interleaving. That is, you can interleave any number of ADCs to increase the speed. But in practice, you will find that as you keep increasing in, the calibration logic and algorithm required to correct for the mismatches in offset, gain, and timing skew, they become more and more complicated. And as a result, in practice, you will find 2x to 20x interleaved ADCs. And obviously, beyond this, it is not impossible to do, but it becomes very difficult and becomes more and more challenging. Okay. So let's stop at this point and continue from the next class.